This program will provide participants with an overall description of the reciprocating screw injection molding machine and its components, and an introduction to the injection molding process. At the end of this program, viewers will be able to identify the various components of the molding machine and their functions, demonstrate working knowledge of an injection molding cycle, explain the procedures involved in machine startup and shutdown, and identify the control parameters that are used to develop an optimum molding cycle. Let's begin with a brief description of the reciprocating screw injection molding machine. Although other types of injection molding machines exist, this is the most popular machine used today. This machine uses a reciprocating screw. The word reciprocating means moving back and forth. The screw rotates as it moves backward. This rotating action creates heat, which melts the plastic. The turning action of the screw conveys the melted plastic to the front of the screw. The plastic is then pushed out of the barrel and into the mold to form the part. In this section, we will discuss the basic components of the injection molding machine. The hopper holds and funnels the plastic pellets into the screw and barrel assembly. Drying units are often attached to the hopper to reduce the moisture content of the material. Moisture will affect processing conditions as well as the physical and visual characteristics of the molded part. Hoppers are often fed by vacuum loaders, which lift the material from storage boxes placed in the processing area. Plastic pellets enter the barrel through the feed throat. This area can become extremely hot as heat from the barrel rises upward. Heat may cause the plastic pellets to cling together and clog the feed throat. Clogging is called bridging. To prevent bridging, a cool water jacket is placed around the feed throat to reduce the temperature. If bridging does occur, a wooden broom handle or plastic rod can be used to break the material free. A mirror attached to a telescoping rod will allow you to peer into the hopper. Under no circumstances should you use your fingers or a screwdriver to loosen clogged materials. Never look directly to this area as material can blow back. The barrel of the machine contains the screw assembly. Heater bands around the barrel can heat up or cool down the barrel. The temperature of the bands is used to assist in machine startup and to accurately control the molding temperature in the feed throat area. To prevent personal injury, avoid contact with the barrel heaters. Never stand on the barrel of the machine. A hydraulic cylinder is used to retract the entire injection assembly from the mold. It also moves the injection unit into the mold to begin molding. The function of the screw is to plasticize or melt the plastic material. In addition, the force of the screw turning pushes the melted plastic to the front of the injection unit. The screw then acts like a plunger and forces the melted plastic material into the closed mold. The screw drive motor is used to turn the screw counterclockwise. Typically, this is a hydraulic motor, but some specialized machines use electric motors. The injection piston is a hydraulic piston that moves the screw backward and forward. The fixed or stationary platen never moves, and the stationary side of the mold is mounted here. The movable platen moves left to right using the clamp cylinder piston. Although there are several types of clamping systems, a small hydraulic cylinder is usually used to move the toggle. The 4 tie bars are used to keep the clamp unit together. However, smaller machines may only have 2 tie bars. Now that you've been introduced to the basic components of the molding machine, let's take a closer look at how the machine works. Plastic pellets are placed in the hopper. The pellets fall downward through the feed throat and enter the screw barrel. The screw rotates counterclockwise while moving backwards. This rotating action causes a shearing of the plastic pellets between the barrel and the screw, creating the friction required to melt the material. 70 to 90% of the heat needed to melt the plastic comes from this shearing action. The remainder of the heat comes from the heater bands around the barrel. The rotation of the screw transfers the melted material to the front of the screw. Melted plastic builds up in front of the screw, creating pressure, which forces the screw to move back towards the rear of the injection unit. The screw stops turning once it reaches a preset position. At this point, the injection piston moves the screw forward. The screw acts as an injection ram, forcing the melted plastic material into the mold. Since the screw is an important part of the injection molding process, we'll now look at it in greater detail and further explain how it works. Since the general-purpose screw can be used to process many different plastic materials, it is the most common screw found in industry. Other more specialized screw designs exist to run special materials, such as vinyl or thermosetting materials. The screw can be divided into 3 sections or zones. From right to left, the 3 sections of the screw are the feed zone, the transition zone, and the metering zone. These sections consist of 50%, 25%, and 25% of the length of the screw respectively. A term used to specify screws is the length over diameter ratio. This ratio gives an idea of the amount of mixing that will take place. The higher the ratio, the more mixing will occur. General-purpose screws typically have an L over D ratio of 16:1 to 25:1. The compression ratio is the ratio of the volume of material in the metering section to the volume of material in the feed section. This ratio is an indication of how much the material is compressing. Typical compression ratios for general-purpose screws are 1.8:1 to 3.5:1. Plastic pellets enter the screw and barrel in the feed zone, where the flights of the screw are the deepest. The feed zone conveys the plastic to the transition zone, where most of the shearing action takes place. Sometimes the transition zone is called the compression zone. In this zone, the flights of the screw are not deep. This allows the plastic pellets to be compressed between the screw and the barrel. The metering zone will melt any plastic that was not fully melted in the transition zone. The material is at an even consistency and in a molten state as it builds up in front of the screw. This buildup of material creates pressure at the front of the screw, which forces the screw back towards the rear of the injection unit. Once the screw has reached a specific position, it is then moved forward. The resulting ram action forces the melted material into the closed mold. The nozzle connects the machine to the mold. Different types of nozzle tips can accommodate various molds and materials. The tip screws into the nozzle and can be changed. Typically, a heater band is located around the nozzle to control the temperature of the plastic melt. In some molding operations, a mechanical shutoff nozzle is used to prevent material from drooling. This provides a positive shutoff as the valve will mechanically stop the flow of the material. Check valves are used on all machines to prevent material from flowing over the screw as it moves forward during the injection phase. The most common check valve used is the slip ring check valve. As the screw moves forward, the slider seats itself against the screw and prevents the melted plastic from flowing back. If the screw drifts forward through the melt cushion during packing, this is an indication that the check valve is not functioning properly. Material tends to collect and degrade in the check valve, causing poor seal-off. A check valve specifically designed for PVC does not block the backflow of material as well as the slip ring check valve. However, PVC does not tend to flow back during injection due to its high viscosity. The mold cavity and core define the shape of the molded part. The cavity defines the outside of the part, while the core defines the internal shape as well as any intricate detail. The sprue bushing connects the machine nozzle to the mold and provides a passageway for the plastic to travel. Opposite the sprue is a circular depression or cold slug well. which captures the first portion of the material injected into the mold. The runners then provide a way to deliver the molten plastic material to the vicinity of the mold cavity. The gate connects the runner to the cavity. Material flows through the sprue bushing, runner, gate, and finally enters the cavity to produce the molded part. The remainder of the program focuses on the injection molding cycle and the machine control parameters involved in developing a continuous process. Injection molding machines operate in one of three modes. The manual mode is used for machine setup. In this mode, functions such as clamp open and close, ejector stroke, material and color changes, and screw rotation can be performed. In the semi-automatic mode, the machine makes one complete cycle. Processing in this mode provides an indication as to how the machine will perform in the automatic mode. Adjustments to such elements as clamp stroke, mold open time, injection pressure, and injection speed can be made to improve processing. This mode is also used for molding of inserts, or when an operator is needed to remove parts during ejection. The automatic mode allows the machine to run continuously. Final adjustments to the mold and pressure controls are made once the machine begins the automatic cycle. Fine-tuning of the process will result in high-quality parts. A fourth mode, the setup mode, is used for mold setup. This mode allows for movement of the clamp when the top gate is open. The clamp will operate from left to right when the front and back gates are closed. On some machines, the front gate and mold may remain open at the same time. Fine adjustments to the clamp can be made in the setup mode. In order to fully understand the concepts involved in the molding process, we will describe one complete machine cycle. The injection molding cycle begins when the mold closes. The screw moves forward, injecting the material through the nozzle to the sprue. The material fills the runners, gates, and finally the mold cavities. Next is the holding phase or packing phase. Here, additional material is packed in until the gate solidifies or freezes off and plastic can no longer be forced into the mold cavities. At this point, additional packing only results in packing of the sprues and runners. The material is then allowed to cool and solidify in the mold. During the cooling phase, the screw rotates counterclockwise while moving backwards. Pellets from the feed throat fall between the flights of the screw. As the screw rotates backwards, the pellets are conveyed along the flights and sheared between the screw and the barrel, melting the plastic. The next shot builds up in front of the screw and is ready for injection. The mold opens, the parts are ejected, and the machine is ready to begin the cycle again. Now that we have completed one full cycle, we will discuss the steps required to start up and shut down the injection molding machine. In this example, we will assume that the machine has been shut down for the weekend. This type of startup is referred to as a cold start. Initial preparation is required in order for the injection molding machine to warm up and reach its operating temperature and to fully stabilize machine components. Allow the hydraulic pump motor to run for 1 to 2 hours before the machine cycle begins. Any auxiliary equipment such as heaters and chillers should be started. The barrel and nozzle heaters should also be turned on. Most injection molding machines have a protective device that prevents the screw from turning until at least one of the heater zones reaches its set point temperature. This protects the screw from any damage that could be caused from the initial starting torque. To begin the molding process, spray the mold with a small amount of mold release. Mold release may not be needed for medical or food applications, or when the cavity has a high surface finish. While in the manual mode, the mold is closed and the clamp tonnage and mechanical settings are checked. The feed throat is opened to allow plastic pellets to enter the screw and barrel assembly. Jogging the screw motor on and off allows for a slow startup of the motor. The screw moves backwards until it reaches a predetermined setting. With the purge guard in its proper position, Reduce the injection velocity to 10 or 15%. Take several air shots and wipe the nozzle drool with a spatula. Bring the injection carriage forward and slowly jog the tip until it sits flush against the sprue bushing. Be careful not to slam the carriage, as damage to the nozzle tip or sprue bushing may occur. Place the machine in semi-automatic mode and allow it to complete one full cycle. Repeat this procedure until an acceptable process has been developed. Once the process is acceptable, place the machine in automatic mode and carefully monitor the process to be sure that the parts don't hang up. Allow the machine to cycle for 10 to 15 minutes. Visually check the parts to be sure they are filling completely and that there is no sink or flash on the parts. Once the parts are visually acceptable, they are weighed to ensure shot-to-shot uniformity. Finally, the dimensions of the part are checked and approved by quality control. When shutting down the process, close the feed throat to prevent any more plastic pellets from entering the screw and barrel assembly. After the machine cycles a few times, put it in semi-automatic mode. After the completion of one cycle, place the machine in the manual mode. Move the injection carriage away from the mold. With the purge guard down, slowly jog the screw forward, repeating this procedure until all of the material has been purged. Leave the screw in the forward position. The mold should be coated with a mist of mold saver. Leave the mold in the closed position, but not under clamp tonnage. Shut down the hydraulic pump and barrel heaters. Be sure to shut down the mold heaters and chillers and depressurize the water lines. Most mold heaters and chillers have a vent button that depressurizes the water lines and displaces water to either the drain or the chiller return line. In this section, we will discuss parameters that regulate the molding process. All injection molding machines are designed to perform the same basic functions. These include clamping, injecting, rotating the screw, and heating the barrel. The machine control parameters used to monitor these functions are pressure, speed, time, and temperature. Typically, the types of pressure controlled in the process are the injection pressures, screw back pressure, and clamp pressure. The first stages of injection will fill the mold. Once the mold is filled, an additional amount of packing pressure is applied until the gate freezes off. Screw back pressure is the pressure at the back of the screw as it rotates backwards. When the pressure at the front of the screw is greater than the screw back pressure, the screw moves back. The clamp pressure is the pressure required to keep the mold closed during the injection phase. Injection velocity, or speed, determines the rate at which the mold is filled. The amount of hydraulic oil being pumped into the screw piston controls the injection velocity. Some advanced machines can precisely control as many as 12 stages of injection speed. Injection time controls the transfer of pressure during the different stages of injection speed. Other time-controlled elements include mold open and close time, screw rotation time, and overall cycle time. The key temperature parameters include the barrel temperature, nozzle temperature, and mold temperature. Most temperature controllers will maintain a set temperature to within a few degrees. It is important to accurately control these parameters to develop a consistent process. Reducing part-to-part variation and improving the efficiency of the molding operation is critical to the success of any company. Ultimately, the key point in any injection molding operation is to establish and maintain a stable process to reduce scrap and improve molded part quality. In this program, we have seen the reciprocating screw injection molding machine and its components, the steps involved in the injection molding cycle, startup and shutdown procedures, and machine control parameters that affect processing and molded part quality.